So today what I want to talk about is actually looking at data pre-processing and cleaning data really. And it's got an emphasis really on damage detection and fatigue, but it works pretty much for any type of time signal type data that we're collecting. So in order to go through this, I want to look at the different sources of error and how we can detect and correct them. So we're going to start off by an introduction to the signal path and look at the sources of measurement errors. Then we're going to look at system errors in particular, so calibration and system faults. These can largely, when we've got them, these can't usually be corrected. Signal noise, on the other hand, that can be. So we'll look at signal noise as well. And then we're just going to have a little focus, just for a few minutes at the end, in the noise in rotating machinery part. Okay then. So let's start with the introduction. So I want to look at, first of all, at two different types of approach. The traditional analog data acquisition device, and in particular I'm looking at errors now like inductive coupling, capacitive coupling, ground loops and crosstalk, and also look at the new sensors, the smart sensors and things like this. Here they introduce a different type of error. So we're also going to look at transmission lag and asynchronous channel phase lag. Okay, so let's have a look. What does the traditional analog route look like? So if we think about it, we've got a sensor and it's attached with usually a fairly long cable and then to our DAC. So our traditional DAC starts off by taking those low amplitude electrical signals and it turns them into essentially a high voltage signal that we can analyze. So our transducer takes a physical measurement quantity, so it could be strain or temperature or something. It converts that into electrical signal. It then sends that analog signal over a cable, which goes to our signal conditioner. That amplifies it, it filters it, and it probably converts current or charge or resistance and things like that to an analog voltage that we can measure. So a big fat signal here. That then goes to the analog to digital converter. This takes that high level analog voltage and this digitizes it into a digital signal which we can then store. And that's done in the data logger. And usually there's a little bit of final calibration that may be done in the data logger as well. As we calibrate sensors, we don't necessarily change the firmware on a sensor, we probably change the DAC to look at the calibration of that as well. So that's usually done in that little box there. Now, with this, there's actually sources of noise that come in that. Well, I'm calling that analog transmission noise, and we're going to have a look at that in a minute. Now, if we look at a new type, a smart sensor, for example, it still has the same elements that the traditional sensor does. It's just that sometimes they're in a different place. So a smart sensor actually has the transducer, and then local to the transducer we do the signal conditioning, the analog to digital converter, and then there's usually a communication network controller. So it could be an Ethernet controller, it could be a CAN controller, and various different things. And that then sends the signal on a digital communication bus along with lots of other sensors. Then at the other end we have our data logger. And this also has a comms network controller to find out the information that's on that network. And then it usually logs that, and it also stores a database as well. The database tells us how to interpret the data. So it's still got the same components. It's just that in a smart sensor, they tend to be more local to the sensor, the transducer. They're not necessarily part of the DAC. Now, both of these give you two different types of error. So let's have a look first of all at the analog transmission type. Now this has got quite a long cable between the transducer and the signal conditioning unit, and it typically has quite low voltages that we're measuring here. So typically it has a low signal to noise ratio coming in, and this is why it becomes susceptible to other types of error. So one of those is inductive coupling. So this is where any changing current in a neighbouring circuit can cause a magnetic field, and that induces an EMF, electromotive force, in our long cable. Of course, engineers for many years have found ways of minimising this. So by using a twisted pair cabling, then as it induces a current in one direction, it actually increases the opposite in the other cable. So a twisted pair will help to mitigate and reduce this type of noise. Another one is capacitive coupling. So this is where the capacitance between a conductor and maybe a nearby power cable, especially if it's an EV or something like that, then this can also start to cause noise. But we get around that by using screened cables, and we have an earth enclosure in our data recorder. And also coaxial cabling as well can help reduce this. But when we use coaxial cabling, I've got a note here to beware of earth looping. So now, what is earth looping or ground looping? It's where our data acquisition system, transducer and DAC and everything, has multiple earth points, and there may be a potential difference between those points, and that actually causes random signal drift in there. So one common thing is to try and ensure there is just one single earth point that we're going to use, so that we don't end up with a different potential difference across the two. And finally, the other type of error that we may get is channel crosstalk. So this is where we've got multiple channels being broadcast very close together in maybe a cable with lots of little cables inside. And in this case, there's a mixture of inductive and capacitive coupling. And it's usually done by poor screening in that data acquisition. But there are techniques like wavelet denoising techniques that can help us here, which we'll look at later. So these are all linked to the fact that we've got a fairly long cable that's transmitting pretty low currents and voltages, which makes them susceptible to external noise. Now, in a digital bus, that's much reduced. But digital buses may help us in overcoming some of those traditional errors, but they introduce their own complexities too. So let's have a look at a few of those by comparing the traditional analog data with a communication bus type. So we know with traditional data, we've got a constant sample rate. In today's words, we'd call that broadcast data. It's broadcast at a fixed sample rate, usually a high sample rate, and we know exactly what we're going to get, and we know when we're going to get it. When we think about bus data, such as an avionics bus or a CAN bus or something like that on a ground vehicle, then it's not a constant sample rate. Most data that comes in on this bus is event driven. It's what we call burst data. It comes in a burst of information all at once. There are other things like channel contention. So channels trying to broadcast over the same piece of wire at the same time. And you'll also get things like heartbeat data. It's just data that keeps coming up saying from a transducer, by the way, I'm still alive, really. It's just telling you that it's still there and it's still functioning properly. So we get quite a bit of data coming in on this single bus, if you like, that we have to think about. The other thing with traditional data is it tends to be complete. So when we've connected it up with our cable, we know that when we start collecting data, it's going to collect data hopefully all the way through the exercise. But with communication bus data, there tends to be holes or lags in the data, so it may become slightly late or it may be missing completely. So when we're trying to do a constant sample rate, we suddenly find that there are holes and we're missing. Store them as not numbers and things like that. And we need ways of filling in those missing data bits, and I'll talk more about that in a minute. The other thing is with traditional data, we've set this up, and so we can choose the sample rate that we want to design our cars or our aeroplanes. But very often communication bus data is used for a different purpose to what we'd originally wanted. So very often we have to make do with sort of inappropriate sample rates, but they're the ones we've got, so that's what we have to use. So we don't usually have control over the sample rate we would like. We have to make the best of what we have. The other thing is, in a traditional system, hey, we're building it, so we'll make sure we've got anti-aliasing filters in there to cut out those high frequencies, which I'm going to talk about in a minute. But in communication bus, it is by definition alias data, so we have to think about how we're going to work with that. The other thing is with traditional data, it's synchronous, so multiple channels we can synchronize in time. In hardware, we've got a simultaneous sample and hold buffer, but in communication bus data, it is by definition asynchronous. No two channels were actually sent at the same time. And also, when we log the data, in our communication bus, we usually log the time at which we wrote that data, not the time at which it was originally sent from the transducer. So again, there are holes and lags in that data too. And finally, the traditional data, we've designed it for our own purpose, so it's high precision, we've controlled it, it's analog when we've got it. Whereas a lot of communication bus data is low precision, so it's sent by very limited sized integers and things like that, which means it doesn't necessarily have the numerical precision. The other benefit though is that there's all sorts of new data on that communication bus, which is really useful to us as engineers. So video, radar, LiDAR, sound, and all things like that we have access to. So in general, traditional data, we've designed it. It's intended solely for the purpose of analysis and design. We've put that unit on that vehicle or on that aircraft. Whereas with communication bus data, in many, many instances, it's really intended primarily for real-time control. In other words, as a designer, we are a parasite living off the data that was originally intended for other people, and we're trying to make the best use of it we can. So what does that communication bus data look like? Well, first of all, if we can imagine we've just got one cable, and that cable can either be held at a high voltage or a low. It's usually held high. And then when somebody wants to transmit, they're sending a bit like Morse code. They're earthing that, so it's going low and repeatedly, and it's like a bit like Morse code that we're sending that digital data. Now, at any one time, only one device can transmit at a time. But on that little row that you see here on the top, what I've got here is this timeline, if you like. And each one of these is a packet of data. If we think about packets of data, it feels a bit like a truck that we've got over here. So when the truck comes, first of all, the cab is like, it's got a license plate on it, a number plate. That tells us who the sender is, or it's the identification of the manifest. And by looking in the database, we can see what data, what payload that particular truck has. And the payload itself, this is where we store the actual information. Now, in some cases, that payload may be a whole datum value for a particular transducer. But more often than not, if it's a long value, it may only be part of the data. You may have to wait for the next truck to arrive in order to finish that. Or, if it's big enough, it may have several data values in there. And that needs to be stored in the database so that we can actually start to see what we've got and decode those integer representations or evaluated values into real data that engineers can use. Now, if you imagine that all of these different transducers are all trying to use the same piece of wire, they need a protocol. They need an agreement of how they send it. And the way that most of these work is that they have a collision-based and priority-based decision. So if we have a look down here, we can actually start to see at the bottom here, I've got a little representation. So normally our bus is held high at a high voltage. And if a transducer wants to send information, it earths it, so it sends it low. And it starts by sending its identification. So let's say I've got one called here ID and it's 5. So it's now going to bring it low and it's going to send 10100 if we're going to represent this, say, as a 5-bit number. They never are, but that's why I've done it here for simplicity. Now, what happens if, just by pure coincidence, two transducers want to transmit at the same time? Well, this one's got an ID of 33, for instance. So in here, let me just get a screen pointer for you. So in here, it's now going to send 1, 0, 0, but as it's sending a 0, it recognizes that the line has been brought low by another transducer, and that other transducer must therefore have higher priority. So at that point, when it wants to keep it and it knows it goes low, it decides that it's going to stop transmission and it waits. And it waits usually either until the message is finished or for a random period of time before it tries to transmit again. So when we look at how things work, they have priorities. So we can see here that in this little bit of a window here that we have at the top, we can start to see first of all that our engine bus decides to transmit some information and we receive it. And then the next one, we've now got the instrument panel sends a bit. We may receive that, but we don't necessarily know what it is. The transmission sends one and so on. But there comes a point, for example, when the transmission is trying to send information, but it suddenly realizes something of higher priority is there. Maybe the brake system, because you don't want the brakes to fail, do you? Because you're receiving your radio station information. So this suddenly becomes a high priority, and so everything then has to wait. And this is why we can get some delays in the system or missing data when data are replaced by new data and are never actually sent on the system. So it's got this priority and collision system. It's really smart, actually. And remember, these transmit data really, really quickly. So it isn't usual that you get this problem, but you have to be aware that it does exist. Now, another type of data you can get is request data. So sometimes our transducers just send a heartbeat and they only transmit it when somebody asks them to. So this is request data as opposed to broadcast data. So in this case, we can actually ask a question of a transducer and get it to send back its packet of information. And again, in our data acquisition unit, we may have to do that to get some of the data coming back. So what this means is that very often only one node can transmit data at a time. So there's this collision, detection and prioritization. What we then got is there's no way that actually two channels can be simultaneously transmitted. So what we do is we mimic what we would do in a traditional hardware data acquisition unit. We run a pseudo simultaneous and sample and hold. So we store data in our register, in our DAC unit, and then we have a trigger signal. And whichever channel data is in there, that's what we store. And we assume that they're simultaneous at that point. It may be that one channel is feeding in data really quickly. So in this case, if you like, we're aliasing that data by downsampling it if we're not careful. Or it may be that one channel is sending data really slowly. So we end up sampling over and over again the same value. So it's very difficult to get an analog value when you've got long periods of constant. So we have to be aware of that. And we have to be aware in particular of that anti-aliasing. So really, really quickly, that's just gone through that signal path and it's showing the traditional things and how we got over those, but it's also showing how, as we're moving into a new generation of digital data acquisition with CAN bus and things like that, how there is a new set of problems come on that we need to look out for. I want to go on now, though, to system errors, so in particular, calibration and system faults. So we're going to be looking at frequency sampling errors, so we're going to be looking at amplitude attenuation, aliasing, phase lag and downsampling effects. Then we're going to look at quantization errors, and in particular overflow and underflow errors. Then calibration errors, so polarity gain, offset and linearity. And we're just going to finish off by looking at signal clipping, saturation and dropouts. And most of these cannot be corrected. We can detect that they're there, but when we've detected it, there's nothing we can do about it apart from go and remeasure it all again. So these are bad errors. So let's start with frequency sampling. So what should we set the sample rate to be? So in my curve here, I've got the red line is analog data, and I'm going to sample it at those blue sample points. Now up here, I've taken the highest frequency of input that I've got, which in mine, I've just got two sine waves added together, one at 5 Hertz, one at 35 Hertz. So I'm going to take 35 Hertz and I'm going to multiply that by 10. So take your highest frequency and multiply it by 10, and that's a good starting point for your sample rate. What that means in fatigue terms is I've got quite a few points in order that I can capture the peaks and the valleys. Because remember, fatigue is exponentially proportional to the amplitude. So it's important we've got enough points to represent those peaks and valleys when we do our rainflow cycle counting. So a factor of 10 is good. Now you may have come across the Nyquist-Shannon rule. And the Nyquist rule says the sampling rate must be at least twice the highest frequency present in the signal. So ideally we need 10, that's what I would recommend. But we cannot drop below twice. So what actually happens, so here I've just got the sample rate just above 10. at 75 hertz, sorry, so just above twice. And the Nyquist frequency is half the sampling rate, and that acts like a mirror. So actually, in this case, it's picking up the 5 hertz, it's picking up the 35. So what it's saying is for every sinusoidal harmonic, I've got 2 data points, and that's what I need to represent those data. However, it's really bad luck at trying to pick the peaks and the valleys. It's just pure coincidence if it manages to. And that's why we would prefer 10 times rather than the Nyquist-Shannon rule. Now, what the Nyquist-Shannon rule actually says is that if we cut this down, so let's now sample at 70 hertz. So now I'm missing the 35 hertz completely. So I can see I've got the 5 hertz one coming in, this dotted blue line, but now there's nothing at 35 hertz at all. I've missed it completely. And aliasing is when we go below that. So now if I reduce this to 60 hertz, which is less than twice 35 hertz, what actually happens is the Nyquist acts like a mirror. It takes those higher frequencies and it doesn't get rid of them. It mirrors them round. So it introduces a false signal at 25 hertz. And if I was to reduce this even further, 0 hertz acts like a mirror as well. So before long, you've got this high frequency noise reflected back and forth until eventually you don't know what's real and what isn't. So this is the problem. This is what we've really got to try and avoid happening. So the best practice, sample at least 10 times the highest frequency of interest. Use an anti-aliasing filter because that will prevent any reflection of the high frequency noise. So Butterworth, Chebyshev, Bezel, it's usually a hardware filter that we'll implement in our hardware analyzer. And that anti-aliasing filter, if it's a hardware filter, remember, will introduce a phase lag. So you've got to also try and avoid differential phases. So if you like, my red signal here is actually the original signal. My blue is the filtered, and it lags back in time. So one important way is that when you're measuring multiple channels, measure them at the same sample rate and pass them through the same anti-aliasing filter. You can downsample them in software later, but it's important that when you've got this phase offset, they've all got the same phase offset. If in hardware you analyze 2 different channels at 2 different rates, then they may end up with a different phase lag in the filter. And that means it's very difficult to start to add them together or perform joint mathematical operations. How do you know that aliasing's there? To be honest, you don't, because an alias signal is indetectable. But there are a few giveaway signs. If you've got a PSD now, power spectral density, so this is amplitude versus frequency if you like, if you know that your signal has gone down to 0 well before your Nyquist, you've got a pretty good idea that somebody's filtered it and there's no extra noise anywhere near Nyquist. But if you see something like it's going up, especially with a sharp gradient, that's worrying. That now means that there may be alias data in there and that data may be reflected back. So that's a problem that we now have to look at. So this is something you cannot correct for. You've got to make sure you've avoided at the very beginning. How about quantization errors? So this is in the analog to digital converter when we're taking an analog signal. So in this case, let's say we've got an accelerometer between plus or minus 50G. And we're going to represent that as a digital signal, a binary signal, an integer. Now, let's say we're going to produce in our signal processing unit, our signal conditioner, it's going to be relative to a voltage between plus or minus 10 volts. So that means we've got a gain. So 50G by 10 volts, that gives us 5G per volt. And now we're going to store that. And I'm going to store that, in this case, in an 8-bit integer representation. So if I've only got 8 bits, that means that I've got 256 actual finite values I can use. So I've got 100G now, plus or minus 50, divided by 256. That means I can only go down to 0.391 of a G. So if someone wants to know, well, what's my acceleration to 0.1 of a G? I can't tell you because that's beyond our resolution. That's our quantization error. Of course, what we might do is try a 12-bit quantization. So now if we've got 12 bits, that's 2 to the 12. So now that gives us a resolution of 0.0244G. So our friend who wants 0.1G resolution can now get it. So how do we know whether we've introduced quantization at the precision that we're after? There's a couple of ways. One, we can zoom into the time history and you'll start to see that there are points where there's no points sort of in between this range. They're always at these set stages. So we can start to see in the time history when we zoom in if we've got quantization problems. The other way, which I find much easier though, is to do an amplitude probability distribution. So if I set my bin width to be my precision, if it looks like this and it's nice and smooth, I don't have a quantization problem. As we start to get down here, for instance, we can see now that we've got values and then suddenly no values. So this is looking like we have a quantization. So I'm asking for higher precision than the data is stored in binary. Now, sometimes you'll read in books that there is a way of overcoming this called dithering. It's not overcoming it. What dithering is adding noise in at a low level such that when you redigitize it, it appears to be better than it was before. But it is just noise that you've added. So it's hiding the underlying effect. It's not actually a good way of trying to correct data. You can't correct it if you've not measured to the precision you want. You can merely smooth it over if you like. Now, linked to that, there's also overflow and underflow errors. So overflow errors is where we've been transmitted a representation, but we've not stored all of the information. So an overflow is where effectively the highest bit we've not bothered recording. So what actually happens is we're recording all the information, but as soon as it tries to engage that extra bit, if we've not recorded it, it drops down. And so what we're actually starting to see is as if it's building up from the bottom again, and then it drops in here. Again, this is easy to see in this diagram. In real data, it can be difficult, but we can usually tell by looking at things like the amplitude distribution, as I'll show you in a minute, for the for things like clipping errors and things like that. The other way is that with this same problem, but this time we omit the lower binary values. So this is called an underflow error. So now we're picking up the higher value, but we're missing the underflow. And that is exactly the same as a quantization error. We've changed our quantization because we're missing the lower order bits in here. So they're the other ones which are all related to quantization errors. Now, another thing we get is calibration. So polarity, gain, offset and linearity errors. So first of all, polarity. When our signal increases, we would expect our measurement to increase as well. And polarity is where we usually have a reversal in that. So as the acceleration getting higher, our signal's going lower. It sounds really easy. It's the most common form of error because it's so easy to solder two wires the wrong way round. The best way to get out of this is spot what's happening and then go and take that channel in post-acquisition and multiply it by -1. You don't want to be taking away apart all of your component and resoldering wires when all you need to do is multiply the signal by -1. So polarity errors do occur regularly, and it's just a matter of tracking them down before you go out and then correcting them in post-process later. But other things can't necessarily be detected. So the gain error is where effectively our signal should be following the red line, but actually our gain's set wrong, so we think it's following the blue line. Again, there's no way we would have known what the red one was, so make sure we get our instrumentation calibrated regularly. The other one is an offset error. So when we do calibration, we usually do it as a gain and an offset. So our offset is we're now predicting higher all the time. So again, make sure it's well calibrated. And then there are certain transducers which are nonlinear in their response, like thermocouples and things like that. So again, make sure that we've got it calibrated so those nonlinearities are properly taken into account. If we've got these errors, we won't know at the time we're reading the data that they're there. So it's really important that we make sure our equipment's fully calibrated. And then finally, the obvious ones are clipping, saturation, and dropout. So clipping or saturation is where we're measuring beyond the full scale of the sensor. When we look at a time signal, it can sometimes be difficult to tell that. But if we look at the amplitude spectrum, it screams out at us, because whenever they clip, we're now seeing lots of these edge effects coming in, and it's telling us that this was our calibrated range, but all this data was outside of that range. So it's a really good way of suddenly finding what they are. Again, you can't correct it, because all you know is it was beyond this value. You don't really know what value it actually was. And then dropout, again, is really difficult on a big signal to see. But if we look at the amplitude spectrum, this is essentially where we've got probably sensor failure. So at some point, it's dropping out and not giving us any values. And we start to see this as a spike, usually at a 0 amplitude. So we're now starting to see that there was frequent dropouts of this. Again, hard to tell in the big measurement time histories, but very clear in an amplitude distribution. Okay, so now let's move on. Let's have a look now at signal noise. So this is noise on a signal. I want to look first of all at Gaussian noise, and then tonal noise, things like AC power line interference. We'll also look at things like transducer resonance and mounting resonance, which is also a tonal noise. And we'll look at low frequency signal drift, and then we're looking at signal spikes as well. So first of all, Gaussian noise. So Gaussian noise is broadband. It tends to be white noise. It's affecting all frequency ranges simultaneously, and it's usually quantified by the infamous sort of signal to noise ratio. How much signal power have you got compared to the actual noise that's on it? And this is a classic case here. This time history that we're seeing here is what we measured. Now this one has lots and lots of Gaussian noise on it, and actually it was originally looked like this time signal. So our challenge is, how do we get from this noisy signal here back to this time signal here, even though the frequency content of the noise overlaps the frequency content of the signal? And this is where techniques like wavelet filtering are really, really useful. So wavelet threshold filtering works in the joint time frequency domain, and its real speciality is it can remove noise even if the noise overlaps with real frequencies. The downside is you could tell a filter that's called wavelets is not going to be easy to use. It requires a little bit of experimentation. Typically they take 5 to 10 minutes to set up, and they work then quite reliably. But there are a few parameters which don't make sort of engineering sense. They're mathematical parameters. But as I say, once you've read the instructions, they work quite well. They're very robust. And one of the things that we've used them for is for things like doing operational modal analysis on helicopters, where we know we've got these booming rotation of the frequencies of harmonic frequencies of the rotor, which dominate everything. So things like using wavelets, we can take out those dominant harmonic frequencies and look far more at what the structural frequencies are for the modes below them. And over here you can see this is a wavelet filter that's removed high frequency noise, look, but it's also removed spikes as well. So wavelets, it's difficult to use. It's not going to be an easy filter, I'm not kidding you, but it's really capable when you have it. Now, one thing that is a lot easier is what we call frequency delimited noise. So things like tonal noises. So tonal noise occurs at a different frequency. So they're not overlapping, so we don't need a wavelet, but we can then need to isolate them. So this is your traditional brick wall filters. We filter out those frequencies that we're not interested in. So things like, if we've got a low frequency drift, then we can correct that either in time domain, or we can see it in the frequency domain and we can put in a filter. So if we know that our signal has nothing below 2 Hertz in it that's real, we can put in a high pass filter and filter out that low signal drift. Similarly, let's say we've got AC power line interference in the UK at 50 Hertz-ish, then this will also be a peak here, and this is giving us a high frequency component. Well, if we know that there's not much here between 10 and sort of 50 Hertz, we can again put in a low pass frequency here and filter out those tonal noises. So this is when the noise is at a different frequency and we can separate them. And the classic ways of doing that is low pass, which allows low frequencies to pass but high frequencies not to, high pass, which is the opposite, and of course we've got band pass and band reject. Now, these are usually drawn as that solid red line. But actually, when we implement them, they're not a brick wall like this. They tend to have a gradient, and we can control that gradient. Initially, you think, well, I'm going to make it as sharp as I can. But that has other effects which will influence our quality of fatigue prediction. So actually, we need to get quite a gentle gradient. So let's have a look at some of these effects. So first of all, this is a filter. It's a Butterworth filter, and it's showing phase lag. So we can see our blue signal is the original, and our red is now lagging. So this is actually a band reject filter. So we can see it starting off, and then it gets to this frequency here where it starts to reject it, and then it comes back out. And we see here we've got this ringing sound. So this is a good indication I've set my filter to be too steep. A steep filter is good in frequency resolution. It's really bad for amplitudes because it literally is like striking a bell. It creates this ringing response which adds very significant extra amplitude, and that can interfere with our quality of fatigue estimate because fatigue is exponentially proportional to amplitude. Now this is a phase compensated filter, so you now notice that the filtered signal is actually compensated, and what I've done here to compensate this, I've used a Butterworth filter and we've filtered it forwards and backwards, which you can only do in software. So what we've now done is we've compensated the filter, but you can still see the ringing. So here, a steep filter sounds a good idea because it gives you fine frequency resolution, but you have to have a compromise because that's at the expense of ringing, and ringing can seriously affect the accuracy of our fatigue results. Okay, let's leave frequencies behind for a minute and just look at signal spikes. So a spike in a signal is usually a single rogue data point, and it's very often due to an electrical discharge or something like that, or a contact problem, or something like as simple as a little screw rolling into an accelerometer suddenly gives you a 50G spike or something like that. It's not real, it's just there, and it's an impulse. So how can we detect those and how do we correct them? Well, there's different types of spike. If it's a high amplitude, like the screw rolling into the accelerometer, they tend to be very dominant in the amplitude domain. So if we look at the amplitude distribution, we see most of our data's here, and then suddenly these spikes are characterized by outliers. So we can actually detect it by setting a maximum and minimum. And once we've detected it, the software can detect it's a spike, and then what it'll do is it will just interpolate between the valid regions. So it doesn't do frequency filtering, it just does interpolation between those values. Of course, not all spikes end up being high in amplitude. Some are much higher than the neighboring ones, but this spike here, for instance, it looks really big, but it's actually lower than this real data over here. So here we can work in either the gradient domain or the rate of change of gradient domain, so the derivative or the second derivative. And again, what we can do is we can look at the probability distribution of gradient or second derivative, and again we'll start to see that the spikes really stand out. And now we'll look at the gradient of the data, and when we've found that gradient we can smooth over it through interpolation. And finally, we can also look at a statistical method. So here what we're looking really at the evolving standard deviation coming through it. And what we start to see is suddenly spikes have gone beyond that running standard deviation. So we can start to spot those on this sort of trending approach. One rule of thumb, although I've covered signal spikes after frequency filtering, do this before you do any frequency filtering. Frequency filtering has the effect of minimizing the spike but making it smooth. It's still a spike, it's still bad data and wrong results, and which can affect your fatigue, but because you've now smoothed it with a frequency filter, it's almost impossible to see that. So always do signal spikes before you do any frequency filtering, because the act of frequency filtering makes them almost impossible to detect using these types of method. Okay. So now let's just finish off by looking at special cases of noise in rotating machinery. So we're going to look first of all at pulse transducer errors. So We're going to look at runt pulses and pulse spikes. And then we're going to look at how do we cope with Gaussian noise in rotating machinery, and how do we do special types of analysis for order analysis. So first of all, when we're looking at a rotating machine, getting the speed is usually a critical thing. We probably want to work out torque and load and things like that, but the speed is important. Now what we're getting is usually these are some form of sensor, like a Hall effect sensor, and what's actually happening is the Hall effect is this tooth passes this, it changes the magnetic induced voltage, and we can pick that up as an analog voltage. And what we do is we put in some thresholds, some cutoff levels. So we look at the peak rising voltage, for instance, and that enables us to find these pulses. And there's the peak dropping voltage. So we can then look at the frequency of those pulses. Now, sometimes what we've got is a pulse spike. So sometimes we've got what looks like a pulse, but it's wrong. It's not real. So we don't have the analog voltage usually, we usually have a pulse. So in this case, a good way of looking at it is actually look at the rotation speed and look for spikes in the rotation speed, just like we saw before. Now, when you've got a spike, if you're looking at the pulse signal, you can actually just do a backward fill on that. Or you can actually interpolate the rotation speed signal that you're calculating. So that are good ways of getting out of pulse spikes. What you're doing is you're saying there's no way this machine could go from 1,000 RPM to 10,000 RPM in under a second. So it's allowing us to do that by looking at these freak responses. The other one is the opposite of a pulse spike, is a runt pulse. So this is where one seems to be missing. Now this could be because we've got debris building up in here, so it gives us a runt pulse, or it could be deliberate, like a location sensor, where we expect the pulses at a rate and then suddenly one's missing, and that's actually telling our system that that's top dead center, for example. So there's a valid reason for this and not. Well, if we want the speed, again, have a look at that spike correction, because we'll suddenly get a drop in speed, which we can interpolate over in that rotation speed time history. So again, we can handle those, and these come up all the time simply because pulse spikes occur regularly, but also runt pulses through debris and location markers as well. Now the other one is rotating, Gaussian noise in rotating. Now we can use wavelets and all things like that we've seen, but actually a much better way is actually to use what we call time synchronous averaging. So we transform our data into the angle domain, because this is a rotating shaft rotating at different speeds. If we know the signal that we're measuring and we've got the speed from our pulse, we can actually start to transform it from time domain, in where the x-axis is time, to where the x-axis is angle. And then for each angle increment, so we may split it into, say, 360 different angles in here, we can actually average between them, maybe over several different rotations. So we're rotationally averaging in this case. And this is a really good way, because Gaussian noise typically has the equal probability of positive noise to negative noise. So when we average them out over several rotations, we can cancel out that noise. So that's a good way of dealing with Gaussian noise. Now, one special kind of noise is where we're looking at order tracking. So order tracking is where, say we've got an engine that's ramping up speed. So this is engine speed here, and this is our time here, and this is our frequency here. And what we're starting to see is we're getting a build-up of amplitude. So what we're seeing here is the second order. This is a typical 4-cylinder engine. So every one rotation, I've got 2 firings. So that gives us this 2 per rotation. But we've also got 4 per rotation, 6 per rotation, and so on. And if we want to find out, well, what is the load that's going into, say, our water pump, for example, we can start to find out what order it is, and we can actually put in what we call a Vold-Kalman filter. So this is an order tracking filter. You tell it what order you want, and you tell it the engine speed, and then it will try and build a bandpass filter that tracks the proper frequency. So this enables us to extract that particular order out of it. So this is, again, a really good way of cutting through the noise and getting the signal that you want. So that's been really quick go through these because I need to keep it down to 50 minutes. So just to finish off, we've looked at these 4 areas. We looked at the introduction, so we looked at the signal path and the sources of error. We looked at types of error for traditional analog DAC, inductive coupling, capacitive coupling, ground loops and crosstalks, and we looked at ways that we can minimise and reduce those. And we also looked at data bus and how that introduces transmission lag, asynchronous channel phase lag. And again, we looked at what it is and how we might have to live with that and deal with it. These are avoidable using best practice, but if they're in there, they're generally not detectable or correctable during the testing. So best to actually design your instrumentation, get it well calibrated and everything else to do that. When it comes to system errors, we're looking at things like frequency sampling errors, so amplitude attenuation, aliasing, phase lag and downsampling problems, which is aliasing basically. We looked at quantization errors, overflow and underflow, calibration, signal clipping and so on. These are largely uncorrectable, but there are ways of detecting most of them. So we do know that they're there, but the only fallback is we have to go and remeasure, which isn't ideal. That's going to be expensive. Then we've got signal noise. Now these are largely detectable and correctable. So Gaussian noise that's a tough one. It needs a powerful algorithm like wavelets to do it, but it is possible. By the time we've got things like tonal noise, power line interference, then that's a simple filtering job. That also covers transducer resonance and mounting resonance and low frequency shift. And we also looked at signal spikes. And then finally, we had just a quick look at noise in rotating machinery. So how do we deal with things like runt pulses and pulse spikes? And then how do we deal with Gaussian noise in rotating machinery and order analysis? And these, again, are nice and largely correctable. Okay, so I think I've finished now. So I'll hand you back to Connor. And if there's any questions, then please let me know now.